I know it's been a long but a cool year if you think about it. We started out with the particle in a box and the tiniest little wave function, and now we're talking about the global climate and energy uses and everything like that. There's not a year in your education that has gone that far in terms of magnitude, something that on the order of an angstrom, 10 to the minus 10 meters, to now something that, spans the globe, and even the universe to some extent. And so I wanted to add this last lecture here to sort of tack on. I had the connection to climate tacked onto the combustion sources because that kind of makes sense. That's what produces CO2, which is a greenhouse gas. And so what we'll talk about today, we will cover what do we mean by greenhouse gas. And have y'all had the weather and climate class? I know there's one here on campus. Yeah, it's a non-majors class, so typically science majors wouldn't take it. So you'll get a little bit of that material. They'll probably go in much more detail. So they probably have a whole module on it, but we have one lecture, so we'll jump in. So again, the first law of thermodynamics about energy not being created or destroyed, the total energy of the universe is constant, and we're converting useful energy into random energy. And as that increase in entropy it helps us with spontaneous reactions, we use that useful energy, and then it eventually ends up as non-usable energy, random energy. And so this is what we have for our U.S. consumption in 2020. And we have all of that rejected energy, and then the energy services, the useful energy that we got, which after we use it, then it goes into the rejected energy pile too. So if we sort of slide this over to the left, we have all of this lost energy. It's not really lost, it's just not usable, and it ends up escaping to space, if you will, in the form of heat or infrared light. Okay, most everything on its way down cascades from UV to visible, and from visible to near infrared, and from near infrared to mid infrared, and then it's escaping to space. And it's that mid infrared region which is like the pressure relief valve of all of the heat on the planet. Okay. Now it's not just the USA, but it's also the rest of the world. And so I've sort of scaled this, our 100 exajoules to the world's 300 exajoules to make up the 425 or so exajoules per year consumed, used, and then emitted to space. And so that's that energy needs to be dissipated and emitted to space. But we're really not the thing that's driving the temperature of the Earth. It's the sun. So the sun, again, hitting the Earth with 5,500,000 exajoules per year. That hits the Earth. Some of it's scattered off, some of it's absorbed, some of it's re-emitted every year. And so I tried to put this to scale, and I realized that we've got about 500 exajoules for humankind compared to 5 million. So it's not even 1%. It's like 0.01%. So it's like less than 1 in 1,000. So if this is to scale, if that's our sunshine number, then all humankind is 1/10 of a pixel. So yeah, so if we have 1,000 pixels on the screen and the vertical, and we're 1 in 10,000, we're 1/10 of a pixel on this scale in terms of the heat that we generate. So it's not our heat that's warming the planet. It's something to do with the greenhouse gas effect. But a lot of people think, oh, we're burning cars, or burning coal, burning nuclear furnaces and all that stuff. That's not the heat that's maintaining, our temperature on the planet. It has everything to do with the sun and the greenhouse effect. Okay. So let's look at the energy balance on the Earth. And so I've got these percentages just sort of to help you stay engaged. I've erased all the energy percentages on your little screen. So we'll go through, and this is the energy balance of that 5 million exajoules that's hitting the planet every year. So 100% of that 5 million that's hitting our planet, 25% is reflected from clouds. So there's your first one. So 1/4 of that is reflected from cloud cover. 23% is absorbed by the atmosphere. Okay, so what kind of things would absorb that? Well, the deep UV, the vacuum UV, is 100% absorbed by the atmosphere. A lot of that creates ions, and that's why they have the ionosphere. So way out in the upper atmosphere, it's knocking electrons off of nitrogen atoms. Below that, it's breaking nitrogen triple bonds and oxygen double bonds and making atoms. So we have atoms and ions out at the, then we have molecules, which are absorbing the vacuum UV. Then we get into lower atmosphere, the ozone layer and so on, absorbing that valence band UV. So all of the UV light is filtered out. That ozone layer protects us with that last sort of near to the visible region UV that would be damaging to our skin. So that's filtering out that. But also some of the infrared light from the sun is absorbed by the atmosphere, by water, CO2, and so on. Infrared's not absorbed by the oxygen and nitrogen because it's a symmetric, it's a homonuclear diatomic. And so the infrared light goes through the homonuclear diatomics and goes through past argon. And so then 46% is absorbed by the surface. I would say, absorb, or maybe hits the surface and then, no, 46% is absorbed by the surface, and then the remaining 6 of that 100% is reflected. So all of these yellow bands are the initial light that comes in. It should add up. So 46, so 40, and then the 23 and the 25. So that's 40, 50, 60, 70, 80, and then there's a 85, 86, 87, 88, 89, 90, and then 5 and 5 is 10, so that's 100. Okay, so it all adds up to 100. Okay, so that's everything that comes in, and you can imagine that changes in cloud cover will change that reflected from the atmosphere. I mean, from the atmosphere and from clouds. So cloud cover is probably one of the most important things in terms of controlling how much heat actually hits the surface. Okay. And then once it's absorbed by the surface, of that 46%, 9% is emitted by the surface. Okay. You say, what are the other bit? Well, 37% is absorbed by the atmosphere. So that 46%, that's 37 plus 9, right? So that 46% is emitted back from the surface, and 37% of that light is absorbed by the atmosphere. 9% makes it all the way out. So there's this open window that lets that light out. The light that is absorbed by the atmosphere, that's the greenhouse effect. So why do we call it that? Well, think about a greenhouse. So I'm going to go ahead and write this here, greenhouse. It's like 2 H's. Let me get it. Okay. So a greenhouse, it's a greenhouse because you've got plants in there and they're green. So the greenhouse has glass windows that let visible light in. The visible light is absorbed by the soil and pots and wood and everything in the greenhouse and the plants. And then it's trying to emit infrared light, and infrared light doesn't go through glass. If it's smooth panes of glass, it's reflected back in. And so that heats up the greenhouse. So even in winter, you can grow plants because that greenhouse keeps it warm. A greenhouse effect. Same thing's happening in our atmosphere. Visible light comes in, it's down converted into infrared light, and that infrared light is absorbed by water primarily, and a little bit by CO2, and then a little bit by other trace gases like methane and everything. Why is the infrared light absorbed? Well, think about your vibrational spectroscopy. You guys actually know what's going on here. Your vibrations, the stretches, the bends, any molecule that has like an asymmetric diatomic like a CO would be a greenhouse gas. CO2, you've got bends, you've got stretches, asymmetric stretches, those are going to absorb in the infrared. So all of those things, anything with more than 3 atoms or anything with 2 atoms where the atoms are not the same would be a greenhouse gas. Anything that has an infrared absorption. The nitrogen and oxygen do not absorb in the infrared. They're so symmetric, they only have a Raman spectrum. So since they don't absorb in the infrared, they're not greenhouse gases. We would not be here if oxygen and nitrogen absorbed infrared light. Our atmosphere would heat up so much with these 5 million exajoules per year of our sun hitting our planet, it would just drive that atmosphere away. It would ionize all the molecules and heat them up and drive them away. And so we would be like one of these planets where just the atmosphere is cooked off. Okay, so luckily the homonuclear diatomics and noble gas like argon, those don't have infrared absorption spectra. Okay, so then what about the atmosphere? The atmosphere is heated up now, so it's got 23% here absorbed on the incoming light, 37% absorbed, and also this greenhouse gas keeps us from freezing at night. So that's what gives us stable temperatures when the sun's on the other side of the planet. So that helps us stay warm overnight. So we've got this amount of energy absorbed in the atmosphere. The atmosphere eventually gets rid of that. And so you have CO2, water, other greenhouse gases, and it's just a statistical thing. Think about it. So you've got a molecule in the atmosphere. Whether it gets light from the sun, it's now excited, and it can emit, and you can just do like a 50-50. It could go up or down. So some of that goes down, it hits something else, but eventually it's coming back up. And if it's like a vacuum or a pump, if it ever is emitted up, it's gone to space. So if it emits down, it'll go down, it'll eventually come back up, and it'll eventually go to space. Since there's no returning force from space, this infrared light just leaves. And that's why we eventually cool down. Okay. So this is the energy balance of our planet. And again, these pumps, that's like 60% of 5 million exajoules or 6% of 5 million exajoules. These are enormous numbers in terms of the energy. So let's focus on how much energy and greenhouse gases our home produces. So we kind of covered this before, but I'll just go through it just so it's on this one video. Again, Entergy Texas uses the typical customer definition of 1,000 kilowatt hours per month. So that's 12 kilowatt hours per year. And so how many gigajoules is that? So we just convert that 12,000 kilowatt hours per year. We want to get rid of this watts and hours and so on, and get to joules. So again, a kilowatt is a joule per second, or 1,000 joules per second. And so we've canceled the kilowatts, and we've canceled the hours. It's 3,600 seconds, and then the seconds cancels the per second there. And so that gives us joules. And then you've got a couple of powers of 10 here, or powers of 10 to the 3. And so that's going to end up with, see, we've got 1,000 here, 1,000 there, and 1,000 here. So that's a billion right there. So that's the giga. So it's 43.2 gigajoules per year. So that's what a typical electrical home customer uses. That's an enormous amount of joules. So a joule must be a tiny little piece of energy. Remember, it takes 4 joules to raise the temperature of water 1 degree. So it's not a lot of energy in 1 joule. So how much coal, natural gas, or hydrogen would you need to power a typical home? And here I've erased some of these numbers too, so to keep you active. So the 43 gigajoules per year, if we use those World Energy Council numbers to convert that to tons of coal, this is 1.47 tons of coal equivalent. So that's kind of a lot of coal. I mean, that's 1 million grams or 2,000 pounds of coal. Now that would fill back of a pickup. I mean, it's not like a house-sized pile of coal, but it would be a good load of coal. It'd be less oil. So 1 ton of oil, not 1.5, but 1 ton of oil. So you see, it takes more coal than oil. And then here's the natural gas. Instead of billion cubic meters, it would only be million cubic meters, and it would be 0.001 million cubic meters of methane per year. And then hydrogen can be about 4 times that hydrogen. But this is electricity that we're looking for. And remember that the electrical generating grid is only about 30% efficient. So let's take into account efficiency. So if we put in that 31% efficient, so now we have to put little subscripts on our numbers. We have 43.2 gigajoules of electric per year. And here's another way to use those efficiencies, is to put subscripts on your joules. So we only get 31 joules of electricity for every 100 joules of heat, or 0.31 to 1. And so we're dividing by 0.3. Essentially, we're multiplying our our usage by a factor of 3. So it would take 4.7 tons of coal if we were using coal to generate that electricity. It would take 3 tons of oil. It triples all 3 of them. So this poor efficiency triples our usage. And the reason I asked this question, does this inform your opinion of using electricity to heat things? Remember, we're not running out of fuel necessarily, but we want to be efficient in its use. And so to try to shift everything over to electricity when we just need heat is a really bad thing. That's they've passed laws. They're trying to pass laws all over the place, the UN and also in our own government, trying to outlaw natural gas stoves. When natural gas stoves are fantastic because you're getting 100% of those joules when you burn it. If you burn natural gas to make electricity, you get about 1/3 of those joules. So they are sort of making up, I think, claims or overhyping those claims of danger in the home. Natural gas burns very cleanly. We've had natural gas stoves in homes, no health effects from the natural gas, more health effects from things we clean with, things we wash our clothes with. I mean, other environmental insults, things we eat, homes of smokers. If you're smoking, you're not worried about the natural gas stove. So, I mean, it's really frustrating to me to know the science and to watch the policymakers make decisions that are going to triple our usage. That just drives me crazy. So then how much CO2 does this produce? Because again, the CO2 is one of the greenhouse gases that has an impact on the climate. So this 4 tons of coal would produce 17 tons of CO2. Where's the extra mass come from? From the oxygen. Okay, so when we're talking about CO2, we're talking about a heavier molecule. The 3 tons of oil would produce 10 tons of CO2, so almost half the amount that coal would produce. And the amount of natural gas only produces 6.8, so almost 1/3. I mean, not quite 1/3, or a little more than 1/3, I would say, CO2 for natural gas. But you can see how attractive natural gas is. And as this country discovered in the past 5 or 6 years, more methane, more natural gas reserves, and we shifted a lot of our power generation over to natural gas, our greenhouse gas emissions have really dropped. So we haven't changed our lifestyle, we changed our energy source. That made a huge impact. So we actually didn't sign like the Paris Agreement or whatever it was, but we met our goals if we had. So it's kind of one of those things. We didn't sign it, but we met the goals of reducing greenhouse gas emissions because of the shift over to natural gas. Now, is this a lot of carbon? Even if we use the 17 tons, it's not when you compare it to the atmosphere, okay? It's a lot if you're trying to carry it, okay? But it's not a lot compared to the atmosphere. So 17 tons, and look how many tons of CO2 are in the atmosphere. 2,700, let's see, what is that? 2,700 billion, okay, tons. So this is the amount of mass of CO2 we have in the atmosphere. It's a petagram of CO2. So peta is 10 to the 15, exapeta, yeah. It's so funny. And that's not PETA, the people for the ethical treatment of animals, but it's the metric prefix, or people eating tasty animals. And so this is the atmosphere containing an enormous amount of moles, and those moles you can convert to grams and so on, just using your normal Gen Chem unit conversions. It's all very straightforward. Now this is the number of petamoles of CO2 right here. Let's see. Gotta find my pen. Right here. This is the number of petamoles of CO2, and this times 10 to the 4th is the oxygen, and times 10 to the 5th is the nitrogen. So let's look at the atmosphere. It's absolutely enormous to think about. So the mass of the Earth, and this is in petagrams, so it's this many times another 15 zeros. And I think that's one thing that I would like as a scientist that you should have a grasp of, is how absolutely enormous our planet is and how enormously stable that is. I mean, I'm all for taking care of the habitability of the earth, you know, but we are not even capable of destroying the earth. We are capable of destroying the habitability of the earth. Okay, so it's I don't personify the earth. I don't like say we got to save the earth because the earth doesn't know we're here. But we can mess up our living room. We can mess up our house, right? We can mess up our neighborhoods, and we can mess up the habitability of the earth. And so that's my own little nuanced take on it. So here's the numbers in terms of petagrams and petamoles of CO2, nitrogen, oxygen, water. Look how much water varies just on a natural basis. You know, if you were to measure locally the concentration of water, then it would be huge, like 1% to 5%, depending on the humidity, the relative humidity. So for the numbers that I've been calculating, I've just been using the 2.5% because it fluctuates. So I just picked the 2.5% number. And so in our mass action table that we'll do in a minute, I use this 4,540 petamoles of water. Here's argon. The CO2 has been climbing, so this is a little bit low. I think it's probably 400 parts per million now, and so that gives us 62.7 petamoles here. And then methane, real tiny numbers. You know, this is a greenhouse gas as well. It has a higher greenhouse global warming potential than CO2, but it's still a very small number. N2O. So the NOx is also very small. Here's some CO, again, a greenhouse gas. Ozone, yeah, it would be a greenhouse gas, but it's reactive at the lower atmosphere. It makes it up to the stratosphere and protects us. On this global scale, these are all zero. I mean, they might be down in the parts per trillion level, but they're very tiny. So let's remember our equilibrium. So if we start with all reactants or all products, the reaction is going to go forward or go backwards. But we're going to reach this point where we're at equilibrium. And if anything pushes that equilibrium towards the reactants or towards the products, it's going to have a restoring force that goes in the opposite direction. That's Le Chatelier's principle. So here's an example out of the freshman book. You've got the Fitzhopper process, and you've got hydrogen, ammonia, and nitrogen. And when it's a steady state, these are coming in and they've reached some steady state. How do you know it's equilibrium? Well, it's reached a steady state. It's going to be at the bottom of that well. And if you introduce something that perturbs the system, like here we jump up the hydrogen concentration, it's really perturbed, but what we put in is not what stays, right? It's consumed and a new equilibrium is established. Now, it did go up, but it came down by quite a bit more than it went up. And the other gases react as well. So that's Le Chatelier's principle. We're familiar with this. And so it may be hard to determine if a system is at equilibrium because you've got, especially in the environment, things are in flux all of the time. But they're in flux because they're trying to reestablish this steady state. And so we could treat it like an equilibrium. So let's do that. This is just a rederivation of that equilibrium connection to Gibbs energy. So you've seen this before. So here's our global equilibrium or steady state. And so I thought, what if we took this 425 gigajoules per year and we just assumed that it was the most CO2 producing fuel? So if we got rid of all the nuclear, all the wind, solar, all of the oil, and we just used coal to generate all of this. That's not just the worst case scenario, that's 5 times the worst case of the Intergovernmental Panel on Climate Change. So I just wanted to see what could we possibly do as humans if we used the dirtiest fuel and generated the most CO2 possible to run the whole planet. That'd be 5 times their worst case. And it would change a fair amount. So here's the reaction for the world in sequestering CO2 into the biosphere. So you see this piece right here, that's plants. Carbohydrates, cellulose, starch, that's plants, okay, the biosphere. And it's taking water, CO2, and light. So photosynthesis comes in and fixes that CO2 into plant matter and produces the oxygen. So as long as we have oxygen, as long as we have water, as long as we have functioning plants, we have a balance with the CO2. If CO2 goes up, what's going to happen? Plants and algae are going to flourish and take some of that out. It won't take all of it out, because just like the hydrogen, nitrogen, and ammonia equilibrium, hydrogen went up a lot, it came back down. It was still an increase in hydrogen, and then the oxygen and ammonia reacted the same way. So there will be a change in the water, change in the oxygen, but those are so huge, we won't even be able to detect their changes, but we will see what happens to CO2. So it's kind of like the limiting reactant in this case. So if we did, again, this worst case, ridiculously worst case scenario here, we could generate 1.2 petamoles of CO2. So that's going right in here. That's the change row in our little equilibrium. And remember, that's the worst case. Okay, so it could go up 1.9%. So if we could move it, that's not nothing. I mean, that's 2%. If we just burn everything in coal and produce only coal energy. But that's 2% before Le Chatelier's principle has a play. So it goes up. And so I thought, let's not make our assumptions like we always do in freshman chem and say X is small. Let's just beat this thing in Excel and go down and change X until we reestablish equilibrium. So here's a minus X on the reactants, plus X. And so we've got the minus X on these pieces, the plus X over here. And so that's what this table is. So if I take 0.8, so if I react 80% of that amount, let's see, where's my pen? Here we go. So right here, I've got like 80% reacted. So if X is 0.97 and I calculate Q, it's not K, right? It's not equal to K. And so we got to increase it a little bit more. So we go up to 1.09. Still, it's gone up. Q's gone up, but it hasn't reached K yet. So we keep going. Eventually, when X is 1.15, we've reached K. So we're back at the equilibrium constant. And so we've consumed most of it, like 98% of it. And we've, even in the worst case of powering the world on coal, we would increase it 0.06 petamoles of CO2. Now, is that something that the world can handle in a year, right? We can calculate that that's the flux we could push into the atmosphere, but can the biosphere grow that fast? And can the oceans absorb this excess CO2 that we've added that fast? And so do you see the question? We could produce that much CO2 in a year in the worst case scenario. And is that something that's going to throw the environment out of whack? Think about this. We have like a bucket of water, and we've got a bunch of pumps that are adjusting the level of that water. How fast are those pumps moving in gallons per minute? We can dump like 0.06 gallons in there, and if the pumps are moving a mil per minute, we've really thrown the system off. But if the pumps are moving in gallons per minute and we only throw in less than a gallon, those pumps can adjust and handle our increase. So let's look at the fluxes in the atmosphere. Oh, sorry. Before we do that, though, let's see what happens with temperature. So like if this does increase our global temperature, what will happen to that equilibrium constant? Well, we can calculate that, right? We know there's a temperature effect right here in our Gibbs equation. Okay. And so we can sort of calculate that Gibbs energy for change for our atmosphere at room temperature. So I just, again, this is just to see what happens if that goes up by a degree. Okay. So then we recalculate K with 299 Kelvin instead of 298 Kelvin, and it actually went up. Okay. Instead of 0.1335, it went up to 0.1344. Okay, what is, if K increases, the reaction moves to the right. And so what was the reaction again? The reaction is here. If the reaction moves to the right, then that's going to chew up even more CO2. And that makes sense too. It matches what our experience is. If temperature goes up, our plants grow better. Okay, they may not grow better right at the equator, but they're going to grow better in Minnesota. And there's a funny group that's been around for a while called Minnesotans for Global Warming. Because it gets pretty darn cold up there. You know, forget the rest of the planet. We want a little bit warmer winters. I thought that was funny. So here's our fluxes. So if the worst case scenario would be that we could put 15 petagrams of carbon per year, that's the max, into the atmosphere, what kind of fluxes do we have? So I went on a search through the literature to figure out what kind of fluxes we have in keeping the amount of CO2 in the atmosphere stable. So here's one, and it's in terms of, instead of CO2, all of these fluxes I found were in carbon, fluxes of carbon. And so if you take the petagrams of CO2 and you divide by the mass of CO2 and multiply by the mass of carbon, then you get the petagrams of carbon. So it's 750 is in the atmosphere. 750 times 10 to the 15 grams of carbon. Deforestation, you hear about that. If you cut down the trees, they can't fix carbon, and so that can release, especially if it's burned, release 1.5 petagrams of carbon per year. But there's also reforestation, and it can suck up 0.5 petagrams of carbon per year. Trees grow well, but they don't grow that fast. Okay, so what grows faster? Smaller plants, like the weeds in my yard, but even more the algae. If you ever see that Planet Earth series by the BBC, oh man, it is great. And they have some time-lapse satellite photos of the Earth. And when summertime comes, the oceans just turn green. It's just incredible. It's like you just see this green color. It's like somebody dumped dye into the ocean. It's amazing. And that's what's going on here with photosynthesis. Look at the flux that this photosynthesis can do. It's unbelievable. And like our 5 times worst case is 1/10 of that. So we can increase the CO2 by a measurable amount, but the pumps in the environment are totally able to handle that. Okay. And then the ocean also about, up to almost a factor of 10 times what we can do. Now, does that mean there's no problem? Well, guess what? As CO2 goes into the ocean, you do see a change in pH, and we're seeing that affect coral reefs and things of that sort. So we see CO2 going into the surface waters, and we see it having some effects. Okay. Also, you raise the temperature of water, and it is the gases are less soluble in the warmer water than they are in the cold. So we get fluxes from the ocean and fluxes to the ocean that kind of match. And so, anyway, that's we change the pH of the ocean water a hair by absorbing more CO2, but the temperature drives it back out. And so it's definitely one of those things that keeps CO2 in check. So the point of this analysis, though, was to see if our worst case emission is enough to overwhelm the pumps in the environment, and it's not. It's 1/10 of the pumps in the environment. So we're not throwing the environment off by the amount of CO2 we can produce in a given year. What we are changing, though, is this number. This greenhouse gas reabsorption number. So let me find it. So this one right here is the one that greenhouse gas number is the one that we're impacting and that we're worried about. In terms of the petagrams of carbon or the CO2, nature is 99% of that number, and our worst case is 1% of that number. Okay, so this is the CO2 in nature that we have, and then our little contribution to it. So what does our 1% increase give us? Does it change this number by 1%? Right, if we increase the CO2 by 1%, would this now absorb 38%? Now that sounds like a small change, but remember it's 38% of 5 million exajoules per year. So that's a huge impact. But here's the absorption spectrum of water, okay? This absorption spectrum of water has only 2 regions where CO2 would be, I say, directly related to concentration. So absorption is directly related to concentration. And if you change this number by 1%, it's going to go up 1% here and 1% here in those 2 little windows. The asymmetric stretch of CO2 and the overtones of that asymmetric stretch, those are already saturated. So we might change the wings out where the rotational lines are. We might have a, out, say, a rotational quantum number, 60 or 70. Those little bands would go up by 1% because they're not all the way pegged. They're not opaque. But the main bands, rotational lines from 0 to, say, 50, they're already pegged. It's opaque there. And so changing the concentration doesn't change the opaqueness. It's already absorbing every bit of light in that small window. So out here on these outer edges, there's 4 narrow areas that are affected by CO2. The rotational wings on the saturated bands, and then the unsaturated bands would be changed. Now that's not 1% of the window though. That's just 1% of that CO2 part of that window. You see, all of these open areas are still open. So statistically, light would still make it out. So we might be able to affect these tiny little windows in our worst case scenario by 1%. And yet we still have these other open windows. Now that's why we are worried about other gases, because they would close some of these windows. Sometimes they hit where water already absorbs. Like this band right here has no effect from CO2 because water already absorbs all of that light. Right, and there's, 10 times more water in the atmosphere than CO2. So we're, that band is already shut by water. Now, I talked about the ocean producing more CO2 when the temperature goes up. And so there's still an argument over whether CO2 is driving the temperature increase, or if the temperature increase is driving CO2, or if this is a positive feedback and forcing. So they call it climate forcing of CO2, where if it raises the temperature a little bit, then the temperature causes CO2 to go up even more. But there is one piece of negative forcing that I think is dominant, and that is this top one. So we know just from Clausius-Clapeyron equation, if you change the temperature of water, you're going to produce more vapor. That's straightforward. And what does water vapor do in the atmosphere? It gets up to the colder levels and it forms clouds. And so that's going to be the ultimate thing that controls this greenhouse effect, is because if we absorb more by the atmosphere and raise the temperature, more water is going to evaporate, and it's going to form more clouds, and that's going to change this number here and this number here. Why more reflected from the surface? Well, because you have more snowfall. You have more clouds. Some of those clouds are in the upper polar regions, and then you're going to start to see more snowfall, and then you're going to increase the reflectivity of the surface. And then you can look back through time that before every ice age, we had a temperature spike. And so you see this increase in greenhouse gases, then you see an increase in moisture, then you see an increase in snowfall, and then you see a drop in temperature because the clouds block the incoming light. And so that's going to eventually happen. Do we want to speed that up? No, not necessarily. But this is, we play a role, but we play a small role in controlling the climate. The largest role is played by this, and that would be the luminosity and flux of the sun. So if the sun changes a tiny amount, then everything we've done to increase or decrease greenhouse gases pales in significance. Okay. So where are we focusing our energy? It seems like we're focusing all of our money and efforts on transportation, like electric vehicles. I mean, it's extremely cool. I love it. But in my opinion, we should be focusing our money and energy on the electrical production, where changing this number here, increasing nuclear, increasing solar, where it makes sense, increasing hydro. I'm just not a big fan of windmills at all. I mean, that's my personal preference. I think they chop up the birds, and I don't think they're pretty. I mean, I think maybe out in Snyder, Texas, there's not much there, but I mean, maybe those guys don't like it interfering with their sunset. I mean, there's something aesthetic too that we should pay attention to, but that's just me. Um, we don't need them. We could increase nuclear and solar without um, putting up these bird Cuisinarts, and then natural gas. The more we could use natural gas and nuclear to replace coal, the better it's going to be. Okay, and so I think that if we're going to have a national um, economic disruption, I think it should go to producing nuclear power. At least in this country, we have the ability to do it safely and securely. I don't see that our increase in nuclear, the use of nuclear energy, increases the risk of proliferation. Uh, and so I think that's the way to go. I'm I'm not for like a cap and trade system to say we're going to cap your CO2 emissions and make you pay an extra fine, because where's that money going to go? Now, the only way I might agree to that is if that money went into the production of more nuclear power plants, right? And that would make sense. But if you're going to just put that money in a slush fund or some sort of false market where they trade CO2 credits, there's a lot of corruption there. There's a lot of potential for a false market where people are going to get away with millions, and there's not going to be any accountability to that. But if we were able to take those kinds of investments and return them back into the power grid, where we actually make some huge gains in terms of our electrical generation, then it would make sense to start working on electrical cars. But if you're trying to just make electric vehicles, and most of your electricity is produced by CO2, producing methane and coal, then now we're just using coal-fired vehicles, and we're throwing away a third of those joules, or 2/3 of those joules. It doesn't make sense. So I think if anybody's talking to you about electric vehicles and climate change and so on, my test is to say, ask them, what do they think of nuclear? And if they won't even go there, then I don't think they're seriously considering all the options. So what to believe? There's a lot of information going around nowadays about this. So read and listen to both sides, and beware of click review versus peer review. Now, peer review checks for blatant errors and flawed logic. It's not a truth blessing. I think we've kind of gotten in the situation of science being like a high priesthood. And if it's been through peer review, it's been blessed, and it's definitely the truth. That's not the way it works. We read through the articles, we look at the data, we look at their conclusions, and we say, yeah, they haven't made any mathematical mistakes, they haven't made any logical errors. The data seems to support what they're saying. So yeah, let's go through. Maybe I would like to see them study more, have more data points or something like that. But we don't get in there and redo all of their math, and we don't go in and like compare it to other data and so on. It's not a truth blessing. And click review is really bad. That's when you've got sort of a clique of scientists that are all in a particular area. And this is definitely bad in climate science, where there's no way they're going to let a paper challenge the narrative. And so that's not peer review, that's click review. Pay attention to those persons who follow the data and cite their work specifically, and pay attention to people who do not insult your intelligence and they react calmly to questions, and ignore persons who only follow persons or cite work nebulously or repeatedly cite consensus. Science doesn't work on consensus. Galileo wasn't following consensus. Thomas, in his experiment on light, wasn't following consensus. Um, and then certainly ignore people who insult you by saying it's too complicated to explain, or the debate's over. Settled science. I mean, yeah, science is never settled. I mean, you got to look into it, and then also ignore people who explode when you ask them questions. And then beware of panels who want your money. Beware of any kind of cap and trade system where the UN is going to end up with the money. They tried this with the oil for food program for Iraq, allowing Iraq to trade oil to feed its population because they wanted to have sanctions on Saddam Hussein, but they didn't want to punish the people. And so the UN monitored or managed this oil for food program, and they walked away with billions of dollars, like persons running the program, skimmed money. And who's going to hold them accountable? They're not under any court system. They're not under any government. And so it's always been, if that's the solution, then I have a problem with the solution. I may not have a problem with the situation, like we have a climate crisis or have to do something with greenhouse gases. Okay, fine, global solution. But putting money in the hands of people who aren't accountable, it can't be the solution. Yeah, so we've got to figure out another way, in my opinion, to deal with this situation. Okay, so crazy final lecture, but helping you kind of put in perspective what's going on right now. And I do not think that we're on the brink of disaster. I just don't. I mean, you can see how much effect